Imagine that we have values of uh, stock rise and stock fall stored in an array. So there's a particular stock and its value rises or falls, and we store that unit in an array, and maybe every slot of that array represents a day. So for instance, in this array, this 15 says that some stock value increased by 15 and then it fell by minus 11, fell by 11. So that's minus 11, then it fell by minus 7, so on and so forth. Now, one very natural question to ask about such data is to find a period in which there was maximum rise, meaning in which there was overall maximum gain. Okay. And then, if that's the question asked, then we are looking for a subset of an array, actually, not a subset, a sub array. We're looking for a sub array in which the sum of these values is the maximum possible. And the problem then becomes maximum subarray sum problem. Now, this problem is also, I just give you one example where we have we need to find a maximum subarray sum, but it's also very widely applicable in other areas. Maybe even in one classical example is image processing. You are often looking for pieces of a matrix or an array that has a maximum intensity in terms of maybe light intensity or color intensity, etc. So all those problems become maximum subarray sum problems. So formally, what is the problem? Let me just go and define this problem formally here, and then we will look at these codes, etc. So if I want to define this problem, the input to the problem is an array, okay, A of integers, and these are positive, negative, zero, with repeats, not sorted. Okay, so an array of integers of size n. So we're given the array and we are given its size, and the output. So this was the input. Okay, the output, and pay special attention to the format of the output because we're going to use this format throughout the algorithm. The output is a three tuple. Okay, a three tuple x. Sorry, I, j, and in fact, let's use characters L, R, and sum. So L is left, R is right, and sum, meaning that the output is a left index and a right index, both included, and the sum of the numbers between these two indices, such that, um, in fact, yeah, I mean, this is the output. Let me just write the such that part in the next line. The goal is that maximize sum over all LR pairs, meaning that, so what is an LR pair? An LR pair is basically a starting index, ending index, meaning actually a sub array. So अगर मैं आपसे कहता हूँ कि किसी भी array की एक sub array बताइए, तो वो sub array क्या होगी? उसका एक piece आपने कट करना है, तो उस piece का एक starting point है, एक left point है, एक right point है. So what we're saying is we want such a piece that has maximum possible sum. Okay, so overall pairs we want to maximize that. That's the goal. So this is an optimization problem, a maximization problem in particular. And this is its input, and this is what our function should return: a three tuple containing the left-right indices and the sum, and it should be the maximum possible sum over all subarrays. Now, in order to solve this, I would like you to, I would say, just pause the video and think of the first algorithm that comes to your mind, because this is the first algorithm that I'm going to discuss with you. So just think about it, pause it, and give yourself some time. Usually when I'm teaching this in class, I ask people some questions and they, come up with ideas. So here you can just pause the video and come up with some idea to solve this problem, and it doesn't have to be divide and conquer. Just write simple loops and solve it. So, I hope some of you have come up with the basic method to solve this problem. Um, so the hint is here. I have to check all pairs, right? I have to check all left-right pairs because each left-right pair corresponds to a subarray. So what I'm saying is, let's consider a very tiny example. A subarray consisting of, sorry, an array consisting of just three numbers. Then this is at index 1, this is at index 2, this is at index 3. So an exhaustive algorithm which wants to check all subarrays has to check these subarrays. 1, 1. Now these are size 1 subarrays, right? Okay, there are all these subarrays. And then there are these size 2 subarrays. Okay. Okay. And then there is one size 3 subarray in this case. So basically we're going for OR LR pairs with obviously L less than R. I mean, checking 3, 2 makes no sense. Also, if you've checked, yeah, I mean, if you check 1, 2, checking 2, 1, it doesn't make any sense because it's the same subarray. So we're going for all these pairs, and if we want to check all these pairs, we can write. I think all of you can write a couple of loops, nested loops, which can produce all these pairs, right? Let's say that this first index it's generated by a loop with a variable I. So for all I need to look at all j, right? And with the extra condition that I is less than or equal to j. You never exceed j. So this is the kind of all pairs that I can generate. So by the way, in this first line, मैंने ऐसी भी सब एरेज लिखी हैं जिनका के साइज सिर्फ 1 है, और ऐसा भी हो सकता है. Let's look at an example. Okay, let's look at this example. Let's say that this is an array. So in this subarray, you could have a situation, for example, this maybe this is a negative number like that. And let me just change this a little bit. And this is like 20. So in this case, perhaps this 20 alone is the best array that there is. Okay, I'm not sure. I just cooked up the numbers, confirm that. Maybe in this case, the total number of elements are 8. So this 8th index, starting indexing from 1, this alone is the best array. If I try to include anything else, I will have to include these negative numbers. Okay, and that will take the sum below 20. I can try to include this 12. If I include this 12, then I have to include, I should include this 1. But then after that, I can get up to this point, and the sum will become 9, right? But then after that, there is all this negative island. So I cannot include 20. So, I think in this case now, the answer is just this one array. Meaning I also have to check size 1 subarrays. Okay, that's important. So yeah, so this is the example we were looking at. And to write code for this, meaning I want to just check all subarrays. सारी subarrays देख लो, सबके sum compute कर लो, और उनमें से जो best है वो pick कर लो. Okay, just pick the global maximum by looking through all options. And that's what this algorithm does. Okay, so if you look at this code, I have written this code a little carelessly, and therefore it is actually, I mean, obviously it's not the most efficient, but even among the inefficient, it is the most inefficient. And we will just now improve it a little bit. But it's a little really simple one. वो कहता है कि आप start कर दें यहाँ से. Just increase the font a little bit. Okay, आप यहाँ से start कीजिए शुरू से, और पहले एलिमेंट को, array के पहले एलिमेंट को जो सिंगल साइज का जो आपकी इंडेक्स है, पहली इंडेक्स, उसको बेस्ट एरे तस्लीम कर लें। सो अगेन, जिस तरह से मैं ये फंक्शंस लिखूंगा, जैसे मैंने मर्ज सॉर्ट भी लिखा था, rather than passing n here, I just pass the left and right indices. So left is the leftmost index, and this is what we are doing here. We're just taking the left, like the element. If left is 1, then I've just taken the element 1. Okay, and I've said कि जो मेरी बेस्ट सोल्यूशन है इस वक्त वो ये है, लेफ्ट लेफ्ट मतलब पहला एलिमेंट, सब एरे ऑफ साइज 1। उसके बाद ये लूप क्या कर रही है, ये वही काम कर रही है कि सारे पेयर्स जनरेट करेगी। लुक थ्रू ऑल सब एरेज ij, राइट, मीनिंग कि आई से शुरू होकर जे पे खत्म होने वाली एरे, तो ये सभी की सभी एरेज यहाँ पर अब चेक हो जाएंगे। और हर ऑप्शन को देखने से पहले एक सम लें, ठीक है। और अब इस पॉइंट पे आपके पास जो आई जे का पेयर है, कि आप इस इन दो लूप्स के अंदर है, तो यू आर वर्किंग इनसाइड एन आई जे पेयर। तो ये एक थर्ड लूप मैंने लगा दी है जो कि आई से लेके जे तक जाती है और तमाम एलिमेंट्स को सम में ऐड करती है, लाइक दिस। ओके, एंड यहाँ पर इस लाइन पे जब आप इफ पे पहुंचते हैं, विच इज आउटसाइड दिस थर्ड लूप, दिस इज इन द सेकंड लूप, दिस इज इनसाइड द सेकंड फॉर लूप। तो अभी तक जो बेस्ट आपने लिया होता है, जो बेस्ट सो फार होता है आपका, अगर आपका नया सम आई जे पेयर का सम, आई जे सब एरे का जो सम है, इफ इट इज बेटर देन बेस्ट सो फार, आप ये अपडेट्स कर देते हैं। आप अपने बेस्ट सो फार को अपडेट कर देते हैं और लेफ्ट एंड राइट इंडेक्सेस को भी अकॉर्डिंगली अपडेट कर देते हैं। ओके, आई थिंक यहाँ पे मैंने थोड़ा मिस्टेक किया, दिस शुड बी जे। So you have left and right pair, the best pair, the best subarray. So this is a correct solution. I think, I hope I don't have to convince you that this is the best solution, like the a correct solution, because, well, I'm just simply going through all the candidates. This kind of an algorithm is called an exhaustive algorithm that just checks, just passes through all candidate solutions, computes the quantity that you're looking for at every candidate, and picks the global maximum. So basically you're finding a maximum. This is finding a maximum through all, by generating all subarrays and generating sums for all subarrays. Now, what is the complexity of this algorithm? So the way I have written is really poor. I mean, it's so this outer loop is obviously going n times, right? This is O of n. And this inner loop is executing for each iteration of the outer loop. This loop also, in the worst case, is going to go to n. So this, just this inner loop and outer loop together, if you look at this line, ये जो sum वाली line है, this is already O of n square, right? This is already O of n square. So but I also have a third loop. So this third loop is again further going another O of n steps, क्योंकि ये जो किसी सब array का size है, it could be as big as n. It could be like maybe n by 2, maybe n by 3 sometimes. So this is O of n also. So this line, this particular line, this is going to execute O of n cube times, right? So, well, this is definitely becoming an O of n cube algorithm. So ये line again O of n square time चलेंगी ये चीजें, but overall यहाँ पर आपका जो time है वो O of n cube हो गया. Okay. तो एक तो ये है कि before, I mean, I'm going to explain to you a better algorithm, which is a divide and conquer algorithm, but you can also improve this algo and bring it down from n cube to n square. That is possible, very easily possible, because you don't need this loop. Okay, so this will be maybe I'll put this as a question, or maybe I'll put it in the homework. This loop is redundant, and you can see why it is. Paying some attention to it, you can accumulate the sum. You don't have to recompute the sum again and again. So actually this algorithm, I leave this to you as an exercise. This algorithm can be made into a O of n square algo. But this O of n square algo is still an inefficient algo for this problem. This problem can be improved, and in fact, the algorithm we are now going to look at is very creative. It's a divide and conquer algorithm, and it will solve this problem in n log n. So just like merge sort brings the sorting problem from quadratic down to n log n, this algo we're going to see is going to bring this quadratic time algorithm back to uh, actually down to an n log n time algo. Okay, so let's go back to this problem, like this slide where I have an example. And before we go into this problem, like into the algorithm, let's discuss some basic, or maybe make some observations about this problem. Okay, first observation is that if you look at this problem for the first time, maybe you would think okay, shayad maybe the largest number should always be the part of the solution, a part of the solution. That's not necessarily true. Actually, if you the way I have cooked up this example, अगर आप इस example में से जरा वीडियो को पॉज कीजिए और इस example में से maximum sub array निकालें, you will see that this 15, which is the greatest element in the array, is not part of that solution. Okay, so it's not necessary that you pick the largest positive element and grow the array around it. That kind of an approach in algorithms has a name. It's called greedy approach, and this is a design paradigm. You can make greedy algorithms, and sometimes they're wonderful and they do amazing things, but in this case greed doesn't work. This plus 15 is not part of the solution. So if you go by greed, often it will fail in trying to solve this problem. Now, and also, by the way, showing you that this 15 is not part of the optimal solution, I have actually given you the proof that greed doesn't work. Because for something to work, for some algorithm to work, it must work on all input. So if I show you even one instance where it fails, I have given you a proof that it does not work. Okay, it doesn't have to sometimes work, it has to always work to be considered correct. So in this case, actually, what is the answer? I hope some of you have worked it out. So the answer here, I think is I think you can combine these and this and up till here. I think this entire thing is the answer. If you add this up, this is 114 back to 9, 20, sorry, 16, 19, 21. I think this 21 is the best answer here. Yeah, I can't include this 15 because then I have to include this entire area. और हम सब array निकाल रहे हैं. Okay, we can't have gaps. I can't say leave minus 11 and 7 minus 7 and just pick 15. That can't happen. So yeah, so and the other thing that you see in this problem is that when I'm looking for the best solution, another temptation in your mind may be don't include negatives in the best solution. That's not really necessary. I mean, इस केस में देखें कि ये -5 यहाँ include हो रहा है, ये -2 include हो रहा है, ये -5 भी include हो रहा है, because in order to include these positives, we have to live with these negatives. Okay, if the net is a positive, we pick that. Okay, so these kind of shortcuts don't seem to be working. Just go to the maximum element, just go to the positive area. So the solution that does work that we have seen so far is just look at all subarrays. So when you're looking at all subarrays in the last algorithm, when I is equal to 4, okay, and when in the outer loop I is equal to 4, and in the inner loop, second loop, j is equal to 11, you will compute this entire sum, okay, and the sum will turn out to be 21, and that will be your best so far, and you would have found the entire array. But then you're looking at all arrays, and that's n square at best. So how do we do divide and conquer on this problem? and basic thinking is going to be the same obviously, क्योंकि same design technique है, तो करना वही है, उसको दो arrays में split कर देना, दो सब problems में split कर देना, और फिर कोशिश करनी है कि वो दोनों का solution मिलाया जाए, combine किया जाए to solve the overarching big problem, okay, the entire problem. How do we divide? Okay, so here we don't seem to have any special criteria on which to divide. So again, we will do our same thing as we did with merge sort. We'll divide it in the middle. We'll compute a middle. We'll have a left and right. From there, we can compute the middle, and we'll divide the array there. So we'll have two sub-arrays. Okay, and again, division logical होगी हमारी, जैसे merge sort में logical हमने division की थी, mid compute किया, और एक recursive call हमारी हो जाएगी इस side की, और एक recursive call हमारी हो जाएगी इस side. Just for the sake of the ease to talk about it, let's say that this is the side left and this is the side R. These are not new arrays. I'm talking about the same pieces of the same array. Okay. So by the way, like in the sorting problem, we were actually changing the array. We had to change the array. We had to sort it. In this problem, हम original array से सिर्फ read करते हैं. We don't change the array. We don't do any writing into the array. We don't rearrange the data. We can't do that. So the array remains as it is. And the other thing you will see in this algorithm is that unlike merge sort, it does not have to create any new arrays. Okay, so it's an in-place algorithm. It doesn't create any new arrays. But the rest of the algorithm is very similar, not exactly similar, but I mean, it follows very kind of identical almost design to merge sort. But obviously there is no merging in this. There's something else. So how do we start thinking about a divide and conquer solution? And you know, one way that you can think about it is basically divide is not something to think about. Obviously divide to hum kar denge, middle nikal diya, divide ho gaya. What you have to think about is how to conquer. How will I use the answers of the sub problems to solve the original problem? And once I ask myself that question, it is obviously known to me कि जो दो सब प्रॉब्लम्स का आंसर है वो किस किस्म का है. इस केस में मैं मैक्सिमम सब एरे सम सॉल्व कर रहा हूँ, तो मेरी दो सब प्रॉब्लम्स भी मैक्सिमम सब एरे सम की होंगी. ओके, by the way, let's give it a short name. Let's call it MSS, so I can write code using that, maybe. Okay, this abbreviation. So if this entire problem is a problem MSS 112, meaning between indices 1 and 12, and this array is A. Okay, so the array A will be passed and 1 and 12. Then my two subproblems are just MSS A16 and MSS A712. And the answers I will get from 16 and 712, if we focus on just this step, that answer will be what? From this left side, I'm going to get the answer कि भाई इस left side की best maximum array कौन सी है, और यहाँ से हमें ये आंसर मिलना है कि भाई ये right side की maximum array कौन सी है. Okay, so given that we have these answers, just like in merge sort we had two sub arrays which were sorted, in this case we can say we have two answers coming, one coming from here, left side, and the other coming from right side. How can we combine those answers and be sure that we have found the answer to the original problem? Okay, what will those answers look like? First question. Okay, will they look like arrays? Will they be numbers? What will they be? In the case of merge sort, they were the two arrays which were separately sorted. Those were like the answers of the two sub-arrays, of the two sub-problems. In this case, the answers will be, again, those three tuples that I talked about. So from the left side, I'm going to get an answer. The left side ki jo best array hai, that has this, let's say L1, R1, yani ki uska left or right side, and S1. Let's call it that. Meaning, left side ki jo optimal array hai, उसका लेफ्ट एंडिंग पॉइंट है L1, उसका राइट एंडिंग पॉइंट है R1 और उसका सम है S1। ये आंसर मुझे लेफ्ट से मिल रहा होगा। और राइट से मुझे आंसर मिल रहा होगा कि यहाँ पर इस साइड पे जो बेस्ट एरे है उसका लेफ्ट है लेट्स से L2 लेफ्ट एंड पॉइंट, उसका राइट एंड पॉइंट है R2 और उसका जो बेस्ट सम है वो है S2। Okay, so these are the answers that I am actually receiving, one from the left side and one from the right side. Okay, and obviously it raises the question, where am I getting these answers from? Well, in a bottom-up fashion from the recurrent process. Okay, so we are again, this is another problem that will be solved in a bottom-up post-order fashion. So when I am at base cases, I will know these answers, and then coming up the tree, I will combine these answers. So for now, I don't need to worry about it. I need to just worry about the following: how will I combine these answers? Okay, and that's an important consideration. So I would say that you should pause the video here again and give it a thought. How will I combine these sorts of answers? What do they mean? And what will be the overall answer then? How will I get it from these answers? In fact, before you think, let me already mention one thing. Ask you a pointed question. What if you get these answers? And what if it turns out that S1 is greater than S2? What does it mean? It means that there is a better subarray on the left side. So as soon as we see that, we already know one thing. This is not the solution. Okay, this may be the solution because it's better than this one. And obviously, if it's the other way around, if S2 is greater than S1, then S1 cannot be the best sum. Sorry, I just messed this up. If yeah, if S2 is greater than S1, okay, then the solution can only be on the right side. Maybe not like, then in that case, this could be the solution. But this cannot be the solution because we already know about a solution, which is this one. The important question that you should think about now is this one. If let's say, let's focus on this thing. If S1 is greater than S2, then obviously S2 is not the solution. The one you're getting from the right is not the solution. My question is S1 definitely the solution for the entire array? Is S1 the solution for the entire array? Remember that S1 is the sum of an array which lies entirely on the left side. Okay, so it's somewhere here, that subarray, and its solution is its sum is S1. S2 is the sum of an array which lies on the right side only. Okay, here you see that S1 is better than S2. S1 sum S1 is better than S2. So अब मेरा question ये कि क्या यही array आपका answer है? Should you just return this answer, or you have to do some more processing before you can merge these answers? Merge, I shouldn't say merge, before you can like combine these answers to produce the answer of the original array. One thing you know, that the smaller number cannot be the answer of the overall problem. But is the bigger number the answer of the overall problem? Is L1, R1, S1 the answer to the original problem, the entire array? So think about that for a minute and then come back to this video. So here's another example for the sake of concreteness. Let's study it. So when you have left and right answers from two sides, so इस case में for instance ये आपका left side आपकी इतनी है और वो दूसरी आपकी right side है, तो जब आपको ये आपकी left side है और ये आपकी दूसरी वाली ये right side की है. So this is subarray 1 4, this is 5 8. Okay, so when you run your divide and conquer algorithm, you get an answer for the best array on the left, and from the answer you should get from the left is 1 2 13. Confirm that this is correct. इधर से आपको आंसर मिलेगा जी कि जो बेहतरीन अरे लेफ्ट साइड की है वो इंडिसेस 1 और 2 के दरमियान है और उसका सम 13 है. दिस इज योर L1, दिस इज योर R1, this is your R1, and this is your S1. Similarly, what you will get from the right is, well, the best array here is, what is it? 6, 6, 14. Okay, because this is index 5, this is index 6. And this array alone is the best, this one size array is the best one on this side. You can check that. If I include anything else, I get a suboptimal answer. So this is your R2, sorry, L2. This is R2, and this is S2. Now you see S2 is better than S1. So definitely this S1 is not the answer. Okay, maybe this subarray is the overall optimal, and this is the answer. But now question is this the overall optimal answer? Maybe it could be, but what are the other possibilities? So now it's an even more concrete question. And if you haven't answered it already, you can pause here again and think again. So just inspecting this array, you will see that there is a better answer for this overall array, which includes all of this, right? If you add all these numbers, this is like 14, 1 added 15, this makes it 8, and this 13, so 21. Overall, this array has sum 21, and it is better than both of these ones. Okay. So why is that the case? Because obviously this answer from the left side is only giving me answers, it's only reporting arrays which lie exclusively on the left side of the problem. Okay. So this is the best answer among this area only. And this is the best answer from this area only. But for the original problem, there are some other kinds of subarrays which pass through the center, and some of them lie on the left side, and some of them lie on the right side. Okay, so let's call these arrays crossing arrays. So there are some crossing subarrays also. And to find a crossing subarray, I will need to look at both sides. Okay, and it just turns out that this is actually the best crossing array that there is. So we have to look at the exclusively left arrays, exclusively right arrays, but we also have to look at the crossing arrays. So if I'm getting an answer from the left and getting an answer from the right, it is possible that one of them is the optimal answer, but it may not be so. I mean, for instance, I can change this a little bit. Let's say that this is minus 13. Let's change this data. Okay. Now I get the same answers from left and right, but now there is no better crossing array. Now this is the best answer. Okay. I can't, because there's this big minus 13 here now, and I can't just include this and also this stuff and hope for something better. So in this case, this S2 is actually the best answer. So I mean, it can happen that one of the two answers, which was the greater one, is the best answer overall, but it can also happen that we have a better crossing array. So I'm going to write a pseudocode based on this much of understanding. And after I write that pseudocode, we'll just go through that pseudocode and we will discuss what are the missing pieces of the puzzle. How do we, fill in those pieces? And then we will do a complete dry run demonstration of this divide and conquer algorithm that we end up creating. Okay. तो इस part को मैं यहाँ पर stop करूँगा because मैंने पूरी problem को आपको समझा दिया है. The next part में I'm going to show you a short pseudocode for the divide and conquer algorithm. And then we're going to discuss one aspect of that pseudocode. And then in the part after that, I'm going to just talk about, basically execute this entire algorithm so that its entire working. Okay. So let's continue in the next part.